Group 1 would now like to present detection of algae in fish tanks using optical absorption. Now we'll introduce our team to you.
Hi, my name is Zia McDonald, and I will be graduating this summer with a Bachelor's of Science in Photonic Science and Engineering. I am looking forward to telling you all about our project.
Hi, everyone. My name is Danielle Naston, and I'll be graduating this summer with my Bachelor's in Electrical Engineering. I currently work at Siemens Energy in continuous improvement, and I'm excited to put our skills to the test and showcase what we've learned over the past 4 years.
Hello, everyone. My name is Keelan McMillan. I'm graduating this summer with my Bachelor's in Photonic Science and Engineering. I'm currently working at X Lumen as an optical engineer, and I'm looking forward to presenting our project to you.
Hello everyone, my name is Virgin Mansour. I will be graduating this summer as well with my Bachelor's in Computer Engineering, and I'm currently working at Northrop Grumman as a cybersecurity system engineer, and I'm super excited to use the knowledge that I have gained throughout the 4 years of school to help assist my teammates with this project.
Our main motivations for this project are to create a design that is both affordable and effective at detecting the presence of algae in water, because the presence of algae in water in large quantities can mean that there are too many nutrients present. Algae characteristics. Algae is a single-celled microscopic organism that thrives in warm, nutrient-rich, slow-moving water. Algae can be detected through the amount of light that it absorbs, or conversely, it transmits. Using the properties of Beer's law and selecting the best source wavelength of light, we will be able to detect the amount of algae in a water sample. Cyanobacteria are a form of algae that contain chlorophyll. If you look to the upper right corner, you will see a graph where you can see that chlorophyll A peaks at 450 nanometers, so we will select that as our source wavelength of light. Cyanobacteria can produce 3 different types of toxins: neurotoxins, hepatotoxins, and dermatoxins. Our basic goals are to design and build a system that uses the difference in input and output light intensity to get the percentage of transmitted light, to design and code a user-friendly touchscreen display, and to keep our budget under $1,000. Advanced goals: design and build a siphon system so that the fish tank can be continuously checked, integrate a thermal camera to check water temperature, and make it Wi-Fi compatible. Our stretch goals are to make an app to go with it, design a system to dispense corrective chemicals. Project description: microcontroller used to power, read, and display outputs. Laser, lenses, and photodiodes used to detect intensity shifts. Thermal camera used to monitor temperature. Liquid crystal display and Wi-Fi module used to communicate with user. Siphon used to draw continuous water sample. Here is a graph of our specifications for our algae detecting system. We have it broken down into separate components. Each component has its own parameters and design specifications. This block diagram shows the distribution of work being done, using different colors to represent each person. Danielle is blue, Keelan is yellow, I am orange, and Virgin is green. Our overall design is broken down into electric hardware, optical hardware, basic hardware, and software. I'm going to pass this to Danielle now so she can tell you some more about some of this hardware.
Thank you, Zia. I'll be taking you through the electrical hardware components for our system. As you saw on the previous page, our system has a few accessories. These include items such as a laser, and photodiodes for the optic system, as well as a liquid crystal display for the user interface. Based off our design, some components will require an analog pin, while others will require a digital connection. Through our research, we determined that the Arduino Uno would be the best microcontroller for our design. The board has a 5 and 3.3 volt pin that can easily be coded using C++ via the Arduino Integrated Development Environment. The microcontroller not only meets our component integration requirements, it also has an extensive online community with countless project examples. Here you can see the schematic of the Arduino Uno. The power supply is at the top, followed by the USB bridge below on the left, and the Atmega 328 microcontroller on the bottom right. Next, we have the power supply for our system. Our design requires continuous power, so a wall adapter was selected as opposed to batteries. Based off the Arduino Uno specifications, we needed input voltage between 7 and 12 volts. We chose the FlickerStar power cable due to its input voltage range and inexpensive cost. The Arduino Uno will receive power through a 6-foot 5.5 mm by 2.1 mm DC barrel plug. Next is our display. First, we had to determine which type of display would be best for our design. After our research, we found that a liquid crystal display would be beneficial for its touch-enabled feature and low cost. Specifically, we chose the Resistive Touch 2.4-inch Nexion liquid crystal display shown here. Nexion has a very similar business model to Arduino in that they both have their own editors with extensive training material to support new users. Virginia and I will have the task of programming the display and then using those variables from that code in the main Arduino code. Next, we have the thermal camera. This will be used to monitor the temperature of the water sample as it travels through the siphon. We chose the MLX 9640 because of its large field of view and easy integration. While this component is on the more expensive side, we lean towards it because we have previous experience on the team working with it. Last, we have the Wi-Fi module. This is going to allow our user to access the device remotely via the internet. The ESP8266 and ESP32 are the most popular ESP modules, with the ESP8285 being a continuation of the ESP8266. Our system is simple and does not require a Bluetooth connection, and based off cost and basic functionality, the Maker Focus ESP8266 was our top choice. Here you can see the schematic for the Maker Focus ESP8266. And that completes the electrical hardware for our design. Next, Keelan is going to walk you through the optical hardware.
We will start the optical components by first going through the optical component specifications, which are the individual specifications for each optical component, followed by comparisons for each component, and finally the optical design. The light source specifications include a collimated beam, operates at 450 nanometer peak wavelength for the most absorption into chlorophyll A to occur. It's possible to integrate its power source easily into a circuit so that we are able to control it electronically. Optical power is no greater than 5 milliwatts to ensure serious injury does not occur. The next component is the beam splitter. The beam splitter's specifications include a visible light anti-reflective coating allowing for more transmission and less unwanted reflections, a 50-50 power split ratio for the split beams to have identical optical power, and a diameter no less than 25.4 millimeters for easy alignment purposes. The specifications for the focusing lens include the same visible light anti-reflective coating as the beam splitter, a focal length no less than 25.4 millimeters but no greater than 40 millimeters to ensure there is enough room between components but not too much where beam distortion may occur, a diameter no less than 25.4 millimeters for easy alignment purposes, and focuses diverging light for refocusing the beam due to any divergence caused by transmitting through water. The last optical component is the photodiodes, where the specifications include an active area no less than 4 millimeters squared, so the alignment remains simple, a sensitivity and/or responsivity of no less than 0.5 at 450 nanometers, and lastly, they are no more than $10 each. The Alpec laser pointer displayed in the left-hand picture was chosen for it operating at chlorophyll A's most absorbed wavelength of 450 nanometers. The power source being a simple pair of easily obtainable AAA batteries, making it easily integratable into a circuit, and for the optical power not exceeding the laser class 3A power limit of 5 milliwatts, at which there is lower risk of serious, potentially permanent injury as long as the beam or its reflections are not looked directly into. In comparison to the big laser pointers brand, at a maximum optical power of 2000 milliwatts, earning it the highest laser classification. At this power, serious injury and permanent damage can result just by indirectly looking at the beam. The J-Ling laser pointers displayed on the right-hand side are similar to the Alpec laser, however the offered wavelengths were inadequate for the final system's design. Instead, they were purchased for preliminary testing and additional stand-in light sources for optical alignment, while the Alpec laser pointer is integrated into the system circuitry. Currently, we are repurposing the green and red J-Ying laser pointers for wavelength-dependent system sensitivity comparison testing in order to establish the most suitable wavelength based on which one results in the highest sensitivity to the presence of low algae concentration levels. The BSW10 beam splitter is 25.4 millimeters in diameter, has a power split of 50-50, and is visible light anti-reflective coated. This means it meets all of the previously described optical component specifications for the beam splitter. In comparison, the BSW10R meets the power and anti-reflective coating specifications but falls short on the size specification and is slightly more expensive. As for the BSF-255-0, it succeeds in affordability, but none of the specifications are met. That leaves the BS-013, which meets all of the specifications, but when compared to the BSW-10, it's twice as expensive, leaving the BSW-10 as a clear decision. For the focusing lens, the biconvex shape was chosen for its ability to focus diverging light, pictured here on the right. The lenses here are all the same besides their focal lengths and their prices, which only differ a little. All the lenses meet the diameter and anti-reflective coating specifications, and the NBK7 material was chosen due to its affordability. As for the comparison, the LB1761A, with a focal length of 25.4 millimeters, is exactly at the lower limit specification for the focal length. It is also the most expensive of the three lenses. Whereas the LB1757A sits directly in the middle of the focal length specification at 30 millimeters and allows enough room for mountings and is slightly more affordable than the LB1761A. As for the LB1027A, its focal length is 40 millimeters, which is at the upper limit for the focal length specification, but is slightly more affordable than the other two lenses. Based on these comparisons, we decided to use the LB1757A in our system to reduce the risks of beam distortion and to allow for mountings to be easily placed in the system. The last optical component comparison is for the photodiodes. We chose the TME photodiodes, pictured here on the left, after comparing it to the following three photodiodes. Photodiode 4 is the TME photodiode and is just under $10 each. The peak sensitivity occurs at 565 nanometers. However, as shown in the graph, the sensitivity at 450 nanometers is 0.7, which is above the minimum sensitivity specification. The active area of 7.5 millimeters squared is also larger than the minimum specification of 4 millimeters squared, which will make alignment simple. Comparing this to photodiode 1, which doesn't meet any of the specifications and has an unknown peak wavelength responsivity, it was obvious to pass this photodiode up. As for photodiodes 2 and 3, they meet the cost and peak wavelength specifications, but don't meet the active area specifications. Due to this comparison, the TME photodiodes were chosen. Lastly, I'll go over the optical design. We start with a laser pointer of 450 nanometers propagating a beam of 2.4 milliwatts of average optical power 5 centimeters to the beam splitter, where it's split into two separate beams of roughly 1.2 milliwatts each. The input beam path is a transmitted path where the beam transmits to the beam splitter and travels 3.4 centimeters to photodiode 1 for the input intensity to be detected. The output beam is the reflected beam from the beam splitter that travels 4.4 centimeters to the first surface of the water tube. The beam then exits the water tube and travels 2.4 centimeters to the focusing lens. The lens focuses the beam 3 centimeters away onto the photodiode 2 for the output intensity to be detected. By detecting the input and output intensities, we can find out how much of the light was absorbed by dividing the output intensity by the input intensity. Next, Zia will explain the optical system testing.
This slide shows how we are going to be testing our optical system. The system will be tested using a sample of hair algae. Hair algae was selected because it is the easiest to identify of the algae. The sample will be at a concentration of 5, 10, and 20 grams per 1 liter of water. The equation for Beer's law, absorption equals molar absorption coefficient times molar concentration times optical path length will be used to get the absorption of light. The absorption coefficient for chlorophyll A in hair algae is 1.261 times 10 to the 5. The molar coefficient was gotten by first calculating the molar number, N, which here in the box below shows the example for 5 grams of algae per 1 liter of water. This value was then taken and put into the equation for molar concentration, as seen below. This slide shows our expected data per 5 grams of hair algae per 1 liter of water. It has the calculated molar concentration, our optical path length, which is 2.5 centimeters, the expected absorption, and the expected transmitted light, which is 1.00056%. That is the percentage of light that will be coming out the backside of the sample. Next, we will be talking about some basic hardware. The first basic component we will be talking about is the siphon. If you look at the image, this is a free CAD model of what the siphon we will construct will look like. It will consist of a constructed water tube, which will be made of 6mm fish tank tubing, 3D printed ends, and plexiglass. The final basic hardware we'll be discussing is the 3D printed components. The 3D printed components will consist of the laser pointer holder, lens mounts and holder, beam splitter holder, and photodiode mount, and also the end caps for our siphon tube.
In this part, we will concentrate on the software design and components, and we will talk mainly about the microcontroller coding and interface as well as the LCD interface. We had 3 different goals for the software component of this project. The first one was the main goal that we wanted to achieve no matter what. and that is program the microcontroller sensors and buttons to make sure that the actual product is functional. The advanced goal that we had for this section is have the machine operate through a touch LCD screen and make a user interface through there. Finally, our stretch goal is, and that is when we have enough time to achieve it, is that we would build an app to control the product through a smart device and make it as user-friendly as possible, as well as send notifications to the users. In order to pursue this part of the project, we had to put together a process of creating the software aspect of this project as it follows. We needed to build the simulation first, and then program the LCD, as well as have an interface board, an app controller, and think about the add-ons and connections. In doing so, we had to have a breakdown diagram of how we're going to proceed and how the software process will proceed. We divided the software process into 3 different categories. We needed to make sure that the device would power on and off, as well as we would be able to control it through the LCD, and then we would worry about the testing part. Like I said, the power aspect of it all, it needs to make sure that the coding would turn on and off the machine, and then we can control it later on through the LCD controller, which means it needs to read the sensors, turning off the system and turning on the system, the I/O, which would be the connection, touch screen, and the app as a stretch goal, and then we would have the code comply and work with all the different types of machines that we have working and all the connections. Also, for it to send notification to the user if possible, and have it as user preference and configuration set for that. Our first major step into coding this project is having the one main code that would make the device operational. And in doing so, we had to set together a pseudocode and plan the type of coding as well as the steps that we need to take in order to build that specific code. We needed first to include the needed libraries, especially the ones that are not there by default, like include Next-Gen, which is the software we would use for the LCD programming. And then we needed to initialize the sensors, declare the Next-Gen objects, which would be in that case the photodiodes, the thermal cam, the Wi-Fi, and laser. We need to program the layout, which in that case would be text, numbers, buttons. We need to register a button object to touch event list. In that case would be the photodiodes, the thermal cam, the Wi-Fi, and laser. After that, we needed to also do a callback function for another button, which when the on button is released, the LED turns on and the state text changes. After that, we needed to initialize another button with a callback function, which is when the off button is released, the LED turns off and the state text changes. We needed to have a slider callback button that we will call H0, and for that specific slider, when the slider is released, the LED brightness changes and the slider text changes. After that, we needed to have another button that would do an update component as a callback function, and that is when the update button is released, the temperature and the humidity readings are updated. Then we need to have an output, and in that case we would have LED lights as the output. And finally, we would debug, run the code and debug any problem when compiling the code, and change anything that would result in errors. We were able to achieve our advanced goal by already programming the LCD screen that we will use. Through using Next-Gen program, which allows us to able to simulate the interface on the LCD as well as program the different functions of the buttons that would show on the LCD. We were able to make a first draft and first attempt at the design that we want. As you can see, at first, this is how the interface looks like on Next-Gen, where we can create different buttons in the interface on the LCD. Our first attempt shows how the fish tank assistant would look like, and we would have the photo diode button, the thermal cam button, the laser, and the Wi-Fi button. And those would lead to the different pages accordingly. So for instance, the photo diode, we have the first page, which was the test, control, and the different numbers that we would set for that. And then the button for going back to the main menu, and so on and so forth. As well as we would have a menu for the on-off button that would turn on the machine and turn it off as well. In this slide, we will talk about the software stretch goal, which is programming the app. The purpose of the app is to notify the user of the levels of algae in the water. In this case, since it is a stretch goal, we are currently looking at the process required to build a simple notification app with an added feature to allow the user to control the device through the app using a smart device. This part's implementation will depend on the time constraint we are under for this project. And in this case, we are using Java in order to see some sample codes on how we can build a notification app to begin with. Administrative information. In this slide, as you can see, we have made two tables to express the budget and financing. The first table shows the budget cost and the actual cost of each system component that we have. And we have successfully stayed within the expected margins. On the second table, however, you can see that we have the financing categories that we have used in order to pay for those components. We have three categories in that table: the total personal contribution, the total awards, and the final personal contribution. For the work distribution, Danielle was in charge of the system design, which is including PCB design, hardware ordering, component testing, and system troubleshooting. For the optical design and system housing, Keelan and Zia worked together on the optical design, optics and hardware ordering, budget and financing, 3D print designs, and Zia assisted with the optical design as well, the housing design, custom water tube design, and 3D printing. For the system software, Virgin, assisted with the coding, component calibration, user interface on the LCD, and user interface through a notification app. We had few design issues, and we are working on finding some of the solutions, as well as we already found some solutions for some of the problems. In the case of the optical design issues, the water tube optical path length of 6 mm, not long enough for sensitive allergy detection. Also, as chosen photodiodes are not sensitive to red light. The solution for that was to design custom square water tube with internal optical path length of roughly 25.4 mm and borrow second set of photodiodes from the undergraduate optical lab. For the hardware design, we are facing the issue of laser pointers overheats and loses optical power after 3 minutes of continuous operation. For the software design issue, we have some compiling errors and must align the components to work correctly with the hardware components, as well as we're looking into some missing libraries that we want to add into the coding. As we are nearing the end of our presentation, we would like you to know our project progress and what has been done so far. For the electrical hardware, all the components have been purchased and acquired. Photodiode testing is complete, as well as the LCD is currently being tested. Optical progress, we have all the optics and optical components have been purchased and acquired. optical components for the additional wavelength sensitivity testing, including red and green light laser pointers and phototransistor, have been acquired. Information on the phototransistors is currently underway. For the software, the skeleton of the microcontroller and the LCD code is done and working on implementing currently. The LCD design draft has been completed and will be modified to suit the goal of making it user-friendly. After taking you on the journey of designing and the building process of this device, as well as reviewing back some of the background research to confirm our theories and methods, we conclude by assuring that we are on track on building this device. And after reviewing the whole process, it is evident that the device we are trying to build is indeed possible to create. All the parts that are necessary to create this device exist, and the theories and physical principles behind it support the fact that it can be built, and once built, will work. We will continue working on advancing this device to be able to use a 450 nanometer laser pointer to measure the amount of algae in a water sample. This water sample will be brought up to the optical system by a way of a siphon. The optical system will be enclosed in a housing unit to protect the user from any glare or reflection from the laser pointer. The device uses the properties of Beer's law to get a ratio of transmitted light through the system to give the present of transmitted light. This concludes our presentation, and we would love to hear some questions. Thank you.